Okay, this is a lecture on impulse and momentum. We have three equations in the data booklet that we'll be working with. One is the definition of momentum, P equals mv. Momentum is mass times velocity. 2, impulse, J equals force times time that the force is applied for, F delta T. And 3, Newton's second law, F equals ma, which originally is written as F equals delta P over delta T, or rate of change of momentum. So let's just calculate some momentum. A 0.50 kilogram ball strikes the floor at 6.0 meters per second, rebounds at negative 4.0 meters per second. Find the initial and final momentum of the ball. Please pause and try to work this one out. And I'm going to work it out now. So momentum is mv, so that means initial momentum is going to be mass times initial velocity. It's going to be 0.5 times 6 equals, initial velocity was 6, it's going to be 3.0, and the units are kilograms times meters per second. P final is just going to be mass times final velocity. 0.5 times negative 4, which is negative 2.0 meters, not meters per second, kilograms meters per second. Kilograms meters per second. Notice that it is negative, and that's because after the ball rebounds, strikes the floor with a downward velocity, it's going to bounce up with an upward velocity, and momentum is a vector. So if you got those correct, you are good. So what is momentum? Let's go through the definition now that we've solved the problem. It's just mass times velocity, and it is a vector. It's equal to the mass times the velocity vector. The units are kilograms times meters per second, which is equivalent to newtons times seconds, which are the units for impulse. And the symbol is the letter P. And it is a vector, so direction matters. If we change direction, we need to take that into account with positive and negative signs. So let's try this again. A 5 kilogram ball strikes the floor at 6 meters per second and rebounds at 4 meters per second. What is the magnitude of the change in momentum of the ball? Well, pause and try to work this one out. And let's solve it. Change in momentum, delta P, would just be the final momentum minus the initial momentum. So our final momentum was the momentum after it rebounded, and we actually already calculated this. So P final is going to be mv, and it was what? It is a mass of 0.5, rebounds at 4 meters per second, so it's going to be 2 kilograms meters per second. 2 kilograms meters per second. And when it struck, it was going at 3 meters per second, so our initial momentum is mu. It's going to be 6 times 0.5, which was 3 kilogram meters per second. Now, one thing that we've messed up here is we changed direction, so we need to take into account the direction change. I'm going to say down is positive. That means up is negative. So that means my initial momentum was positive and my final momentum is negative. Now I can plug into the equation and see that my change is going to be, well, final was negative 2 minus my initial, which was 3. My change was negative 5 kilograms meters per second. Is that an option? Well, the magnitude, it's asking for the magnitude, so that would be the absolute value. 5 is my answer. So especially when we're talking about changes in momentum, taking into account direction is very important. If we didn't take into account those negative signs, we would have gotten the wrong answer. How about this? With what velocity must a 0.53 kilogram, so that's the mass, softball be moving to equal the momentum of a 0.31 kilogram baseball, maybe I'll call that M2, moving at this speed? And since this is the speed of the baseball, V2. Pause for a minute, try and solve this one. Okay, let's solve it. So we want to know the velocity, so that's the velocity of the softball, I'll call that V1, such that the momenta are the same. So it's telling us equal momenta, so I'm just going to write that. P1 equals P2. And now I can substitute in my equation for momentum for each one. P1 is going to be M1 V1. P2 is going to be M2 V2. So M1 is 0.53 times V1. M2 is 0.31 times 21. And I solve for v1, I get 0.31 times 21 over 0.53 equals 12.3 meters per second. There we go. That's the speed we need for our momenta to be equal.